Hello, today we will develop our first real numerical methods. And we start with a problem that looks very simple on the outside. We have a function, we have a point, and we want to find the derivative of f at a. Here we go. Now you passed your calculus 1 course and you say, okay, there's no problem, is there? I mean, you take f, you differentiate, there are some formulas for it, some procedures, and then you substitute a, voila, here is the answer. Well, there is a problem. This function f need not be given by a formula. And if you have a function without a formula, then the calculus 1 tricks are useless. Function without a formula, could it happen? Easily. Imagine that a describes my position along the blackboard. Let's say that 0 is here, something like 10 is over there. You know, there is a nice coordinate system, one-dimensional. I'm walking here, I'm walking right, walking left. F describes temperature. I'm here, and perhaps it's a little bit warmer compared to the position here, because I'm here close to the window and it's around 0 outside. Okay, so I can expect some temperature gradient happening here, and I really doubt that there is a formula for it, because life is very complicated, and very often it is too complicated to be captured by a formula. But those things are happening. So how do I get f at 1? Okay, I go here and I get a thermometer and I find out the temperature. That's how I get the value f at 1. So getting a function value can be actually fairly expensive, which, by the way, is an important consideration in numerical analysis. When we are developing methods, we are, among other things, trying to keep the number of function evaluations as low as possible, because it's expensive. When I say expensive in mathematics, I usually mean expensive in time or in work. That's the two things that we have to pay with, our work and the time it takes. So, but it's not a consideration for today. So let's go back to our problem. We have a function and we just imagine that we can evaluate it, but not by putting in a formula. Evaluate it in some way. And we are interested in the derivative. How do we get it? Well, we do go to calculus 1 after all, and we pick the definition. Here is the version with h. In the numerical analysis, we prefer versions with h, and we will see shortly why. Here we go. So the calculus 1 was actually useful after all. Isn't that nice? Okay, that's a theoretical formula. There is some limiting procedure and so on. But here is an idea. I'm interested in the derivative. Okay, I give up on the idea that I get it precisely. But if I want it just approximately, which is enough for engineering and so on, I can just pick some h, which is really small, put it into this formula, and I get some estimate. Okay, here we go. F prime at a is approximately, this is like a drunk equality or fuzzy equality, and it doesn't have a precise meaning. In this course, I'm using it to indicate that there is some approximation happening, but I don't know exactly how precise the approximation is. So this is just like a fuzzy expression or something like that. Here we go. This is, by the way, called forward difference. I will put up a slide shortly, so don't worry about it now. So how does it work? Somebody gives me a function or a procedure for a function, how to generate the values. Somebody gives me a and asks, okay, find the derivative. And I pick some small h, let's get to it later how to pick it, and substitute into this ratio, evaluate, calculate, and get the answer. And I say, okay, that's the approximation for the derivative. It looks good. Some important considerations. First of all, in the numerical analysis, we prefer h to be positive. Why? Well, because it's an indicator of quality. You can sort of imagine, and again, that's an idea from calculus 1, that when h gets smaller and smaller and smaller, then the approximation of the derivative by this ratio gets better and better and better. It may not be exactly true, but it's sort of true. Okay? So H is an indicator of quality, and negative quality. It doesn't quite sound good. Okay? And there are some other considerations as well. So in the numerical analysis, typically H is positive, almost always. H is positive. In practical applications, not in theory. Here in this theory, H can be negative as well. We will get to it soon. So we have an indicator of quality. We have a procedure for estimating the derivative. Let's see how it works. Do we have room somewhere? Okay, here. Example. So I'm going to look at the derivative of the exponential at 0. Now, why am I looking for it? It's easy, isn't it? Well, that's exactly the point. We know the outcome. How much is it? Derivative of exponential, I put 0 here, and I get 1. I almost slipped there, didn't I? Okay. Now let's see what computer thinks about it. So first we read the exponential function, then we read the 0, that's the point A. Now we ask for the derivative because the computer can do it also symbolically, and computer found that it's 1. Yeah, it's 1. Good. Can we make it even larger? Oh yeah, we can. Okay, so there is 1 here. Very nice. And now we are going to plot, and that's the interesting part. We are going to plot the value of this fraction for different values of H. So we'll make a graph of it. We can see this as a function which depends only on H, which it actually is, and plot the graph of it. Here we go. Bang. Well, I guess you can see it. Perhaps I can enlarge it a little bit for you. Voila, here we go. What do I see? Well, when H is large, like 1, then the answer is not exactly close to 1. Yeah, that's to be expected. But as H is getting smaller and smaller and smaller and smaller and smaller, the value of the ratio gets closer and closer to 1. Yeah, that's a very nice picture because the exponential is very nice. It's a cute function, isn't it? So for other functions, the picture may not be as nice, but the general trend should be the same, essentially. This ratio should tend, well, after all, we know it from calculus. The limit procedure should work. That's very nice. Now, key question. How much can we trust our answer? Because we actually do not provide a formula or a graph. We provide a number. So we pick some H, we substitute, we get a number, and we give it to our customer. Now, the customer actually has some expectations about precision. If you are building a log house, you don't care much about precision. If you are building a watch, you are much more picky. So every customer has a specification how precise the answer should be, or the approximation rather. So how do we get it here? Well, we need to have some idea of the error that we make. That's a very important consideration for numerical methods. So this is our first numerical method, forward difference. And now let's analyze it, okay? What is the error? We talked about it in the introductory lecture on numerical methods. So that's the first important step. What is the error? Well, let's have a look at the picture. Here we go. This is actually a plot of the error. It seems that the plot is negative. How come? Well, let's recall something. The error, and now it's the error of the derivative. So in the notation from numerical that we introduced last time actually, we should put the derivative here to indicate what we are estimating. And now it also depends on H. But people typically would just write EH. It's a slight abuse of notation, but it's okay. So how much is it? It's the exact value minus the approximate value. That's what we had in the definition. Now it is actually the precise value, which is the derivative, minus the approximating ratio. That's how the error looks like. Let's have a look at the previous graph. When we look at it, we can see that our approximations are larger than 1. So we are subtracting something which is larger than 1 from 1. So yes, the errors should be negative. That fits. So this other graph, it looks okay. It makes sense, at least. That's a good news. Now, when we look at it, let's enlarge it a little bit, we can see a curve. Okay, what can we say about it? Well, probably not much. It's some curve. However, typically we are using those approximating methods when the step of the method, this is called the step of the method, is very, very small because we want a small error, so we use small h's. So let's focus. We can see the range between 0 and 1 on this graph. H ranges between 0 and 1. So let's change it. Let's just look for h's between 0 and 0.1. So we're essentially zooming in on this original part of the start of this graph. And when I zoom in, it sort of flats out. It looks like a straight line, doesn't it? What if I zoom in a little bit more? Yeah, it looks like a straight line. So this is very interesting. It seems that the error for small h's behaves like a straight line, which is very nice because it allows me to sort of make some guesses, to let's say guess how it will behave if I change h a little bit. I can adjust it perhaps using this knowledge and so on. So that's a very good question. And how do we prove that the error behaves like that? That's a key question. I talked about it in mathematics. We prove things. Well, let's have a look at the error. Where do we get it? Interesting idea. I see f a plus h here. And in the previous lecture, I have been praising the Taylor expansion as a very good tool. Let's try it. Taylor expansion, fa plus f prime a h plus 1/2 f double prime a h square and so on. Will I need it? Probably not. Okay, there are some higher powers of h, and which of these is dominant around 0? The lowest one. So this is oh cubed. See, that's the convenience of the big O notation. It hides the tail of the series, or the tail of the expansion. Okay, what will I do now? I'm going to move fa to the left. And when I do it, the dominant term will be this one, f prime a, f derivative a, times h. So I'm going to divide by h as well. I will save some room by doing 2 steps in one go. Okay, I subtract it. That's done and dust it. Now I'm dividing by h. So I will get f prime a plus 1/2 f double prime a, just h, plus o. And now I imagine there is this tail of the expansion. It's a infinite polynomial with powers. The dominant one, the smallest one, is h cubed. But now I divide everything by h. So all the powers go down by 1, and the dominant one will be h squared. Okay? Very simple. Okay. What else can I do? Okay, here's the formula. That's the formula for the error. So if I want, one possibility is to rearrange it. Let's see. Okay, I will move this one to the right, the tail goes to the left, and then I switch sides. Okay, what do I get? The error is f prime a minus this ratio, which is, how did I do it? I moved this to the right, this one to the left. Minus 1/2 f double prime a h plus oh squared. Now we say, okay, how come that it's plus? Because I'm moving it to the other side. The answer is, okay, there should be minus here, but then the minus can be included in this big O notation again. I take the minus and I distribute it into my polynomial, and it changes the coefficients, not the powers. And it's traditional to put plus. It looks nicer. Addition, from mathematical point of view, is a more friendly operation compared to subtraction. So I'm putting plus because I like it better. Okay. Here is the formula for the error. Now, what do we take from this? Well, 2 things. First of all, when I look at this, and perhaps before I do that, let me show you a little shortcut. I recalled here the formula for the error. It goes like that. Now, let's rearrange this equation so that it resembles the thing that we have over here. So on the left, we have the approximation. So I move this to the left. On the right, we see the object that we are approximating. That would be the x. This would be the x hat. And the error moves to the right with negative sign, which means if I compare it, if I fit these two formulas, that this tail over here is the negative error. This is actually how I like to do it. That's how I like to play it, because then I don't have to rearrange anything. I just fit these two formulas, and I can see immediately what's the error. This tail is the error, but with the opposite sign. Okay? Anyway, let's have a look at it now. Here is a polynomial hiding. It's an infinite polynomial in quotation marks. I don't care. The important information is that the dominant power near 0 is h squared. But now I add it with another polynomial with dominant power h. This one wins. So one thing I can conclude is that the error is actually OH. And that's a very important information. It tells me that when I'm making h smaller, then the error goes down proportionally, which is good because it means that the error goes to 0, but it's bad because it's very slow. Linear, we talked about it earlier. This is not very convenient, but okay, it's still better than nothing. So I'm happy, reasonably happy. By the way, this also means that the error can be estimated by some constant times h. Now, this c is given, but it also works only for step size bounded by some k. So when you go to definitions of capital O, you will see that it goes like that. There exists c, and there exists capital K, such that we have an estimate, and so on. Okay, so there is some logic behind it, but from practical point of view, this is also useful, with the understanding that it only works when we are near the origin with h, which is something that we see over here. Finally, when I look at this, I noticed that h is dominant, that this tail is comparably negligible when h is really small. This tells me that the error can be approximated. Now, this is approximation. I talked about it earlier. This is not some fuzzy, vague thing like this wavy equation here, wavy equality. Here I didn't really care how precise it is. It was just an idea. This is precise mathematical statement. When h goes to 0, then the error behaves exactly the same way as negative 1/2 the second derivative at a times h. So if we need to approximate the error, we have a formula for it. Now, of course, from practical point of view, there is a little problem because we don't know the derivative. How do I know that we don't know the derivative? Well, because we are approximating it. Would we do all this work if we knew the derivative? Of course not. So we don't know the derivative. If we don't know the derivative, then we don't know the second derivative either. But actually, this can be used in mathematical derivations of more advanced methods. So this is a very useful information. Let's think about our example. In our example, we had e to x, that was our f. So the second derivative, of course, is again the exponential. So the second derivative at 0 is 1. And therefore, the error can be expected to behave like negative 1/2. This is 1, negative 1/2 h in our example. So let's test it. Let's see whether it works. Okay, do we have a comparison here? Not really, so I'm going to introduce one. Here we go. First, I'm going to look at the global picture to also see this curving business and so on. And now I'm going to introduce another function into the mix, and that's negative h divided by 2. Is that it? H divided by 2, exactly. And just to have some better idea of what's happening, I'm going to ask for color. So the actual error will be red, and the linear estimate, 1/2, negative 1/2 h, will be, let's say, dark blue. It's called navy here. Fire up. Okay, here we go. The actual error of the approximation is a curving curve, okay. And the blue, that's the straight line, negative 1/2 h. And you can see that there is a big difference over here when h is equal to 1. This is to be expected because when h is equal to 1, then this tail actually starts also playing role, because these higher powers will be about 1, so we cannot say, okay, that's negligible. That would not be true anymore. So this difference here, that's exactly the tail. But as h is getting smaller and smaller and smaller, then it's true that this O term becomes negligible compared to the dominant term, and we get a better match. And let's have a look again. Let's zoom in. Let's say zoom into 0.1. And you can see that the match is really good. And I zoom a little bit more. And it's really hard to tell those two curves apart. I don't see it there. On my computer, I can see some red pixels protruding slightly down here. So there's actually two curves. I'm not cheating. It's not just one. There's two, but they match really well. So you can see here on a admittedly very nice example that the theory which we developed here actually works. And it does work, because we proved it. Taylor polynomial, this is mathematics, proved. Okay, very nice. So this is a very simple example, and actually people do not really use it much. This is a nice method, but as a standalone method, this is not massively useful, but it is very useful when deriving other, more advanced numerical methods. So it's like a building block, and we are using it here because we will need it as a building block later. That's one thing. But second thing, we can nicely illustrate the important features of numerical analysis. So this is the error analysis, an important part of numerical mathematics. When you discover a new method, the first question you ask is, how good is it? What can I tell about the method? And the typical outcome is like that, or perhaps like that. These are two very useful formulas. They tell me something about the behavior of the error. Okay, let's talk about some problems. Perhaps the most pressing problem of the forward difference is that it's biased. What does it mean? Well, we saw it in a graph before, that it was overshooting. No matter what h we took, it always overshot the correct answer. There is a reason for it. Imagine that you have a function, and let's say that here is a, and you want to approximate the derivative, the slope of the tangent line. You decide to use the forward difference. So you pick h, which is positive, so it moves you to the right. That's why it's called forward difference. You go forward. And you look up the value of your function, you connect, and you look at the slope. That would be the forward difference. If your function is concave up, then this forward difference will always overshoot. You can see it from the picture. The actual tangent line is somewhere here. It has a much smaller slope in my picture. Now, why is it bad? Because if you use it several times for a concave function, then all these errors will be negative, or the approximations will be too large, and it means that you will accumulate errors. If they have always the same sign, there is a good chance that they will accumulate and become larger and larger in your calculations. This is not very good. We actually prefer errors which change signs sort of randomly, if you want. They are sort of evenly spread, pluses, minuses, and then there is a good chance that they will cancel. Okay, in the definition, we also allow for negative h's, which means we are allowed to go back. So let me add it into my picture. I would be also interested in the slope of this one, and this one undershoots. So that's a nice, let's say, companion to the forward difference. This one we would call backwards different, or back different. How does it work? Well, the derivative is more or less equal to, and let's think how we get it. Well, we want h positive because that's a step, but we want to go backwards. Well, in that case, we use a minus h. That's easy, isn't it? And now we can just figure out the triangle here, which gives me the slope. Or, that's another idea, we could put here negative h and negative h into the formula and rearrange it slightly. So we get this. fa minus f, a minus h divided by h. Here we go, backwards difference. And we could do now the same error analysis And we find that this backwards difference has more or less the same error. Just the sign will be different. This one overshoots for concave functions. This one undershoots by the same amount. So when you ask about the quality of approximations, then these two differences do not really make a difference. You can use the forward one, the backwards one. The reliability will be about the same. They are really like brothers and sisters or whatever, twins. So that's not really a big improvement. However, this estimate overshoots and this one undershoots, or the other way around. If your function is concave down, you can see the picture. This one will give you smaller approximations. This one will give you approximations that are too large. Yeah? Either way, these two make errors. They err in opposite directions. So what happens if we take the average? That's an interesting idea. Well, how does the average work? You take this one and you add this one. Average is you sum up. And then you divide by 2. What do you get when you sum them up? You are summing up the numerators. Fa cancels. And you get Fa plus h minus Fa minus h. You divide it by h. And then we divide by 2 because it's the average. Here we go. Now, when I look at this, and I look at a picture, which we will see in a second, I think, okay, symmetric difference, that should be the name. Yeah, symmetric difference. If this one is forward, this one backwards, this one is symmetric. No, it's actually central difference. I have to say I have a trouble with the name. Not that I don't like it, it's a nice name, but I feel it's symmetric. Sometimes it slips in. So if I say symmetric difference and I don't catch myself, please, I beg for your forgiveness here. Anyway, I will try to talk about central difference. Okay, how does it look like? When you look at it, this is a slope again. You can see the vertical displacement, horizontal displacement. It's over here. It's a connecting line or a secant line between this point and this point. And you find a slope, and from the picture it seems that this slope is almost parallel to the tangent line, if I draw it properly. I mean, they are much closer. Okay, they are not quite parallel, but they are much closer than the forward and backwards estimates. So this looks much better, like a much better estimate, which would be wonderful. And notice that it only uses 2 evaluations. This one also used 2 evaluations. So I talked about it, that this could be a major work to get those function values. We are not really doing any extra work here. 2 evaluations, 2 evaluations. So for the same amount of work, we seem to get a much better estimate. And it's true, actually. Let's talk about the error. Now, we are not going to get the error just by looking at a Taylor expansion, because there is actually 2 things to expand. Let me introduce an interesting idea, an interesting method. When we were deriving, or when we are calculating the forward difference as an approximation, we are using 2 pieces of data, also here. Here, we are not looking forward, we are not looking backwards, but we are looking both ways. So there's actually 3 pieces of data available. And when you have more data, you expect better result. Let's have a look at these 3 pieces of data. We know Fa, we know Fa plus h, and we know Fa minus h. Now, I'm going to expand them using Taylor expansion. It's a really good tool. Okay, this one we know. Fa plus f prime a h plus 1/2 f double prime a h square. Do we need more? Where to stop? That's a good question. Let me do one more step. It never hurts. Well, it takes time, of course, and time is money. So I'm going to spend my money here on another term of the Taylor expansion, and I think it was worth it. Anyway, let's talk about Fa minus h. It's actually the same expansion like here, just instead of h, I'm substituting minus h. So, minus h here, okay, minus h here, and the sign comes out, minus h here squares, so the sign stays the same as before, minus h cubed, so there will be minus coming out, and so on. You get a message. You get a picture. Now, notice that the tails here are different. Here, the signs are always plus. Here in the tail, the signs are alternating. So this OH4 should not be taken literally as a specific object, which is the same here, the same here. No, it's a common name for a group of polynomials, of infinite polynomials of tails, and they share the same property. The major power is, or the dominant power is h to the power 4. Okay? So that's how we should understand it. Okay, what is the Taylor expansion of fa? Well, it's just fa. It's a constant function. It does not depend on h, so the Taylor expansion is just perfect like that. Now, these are the three pieces of data. And I want to combine them to get the best possible approximation for my derivative. How do I combine them? When you say it like that, how do I combine them? You cannot really do anything because you can combine them in infinitely many ways, which are some are crazy, some you don't even think of. So let's make our life much easier by introducing just a linear combination. Okay, I will be considering just linear combinations of data. Why linear combinations? Because they are easy to evaluate. And if it turns out that it's not good enough, then I will perhaps start considering more complicated formulas. But linear combinations, let's think about them. Okay, so how do I want to play it? Let's say like this. The first one, the first piece of data is multiplied by A. The second piece of data is multiplied by B. And the third piece of data is multiplied by C. What do I get? Well, this should be easy. I just imagine that this row, this equation is multiplied by A, this by B, this by C, and I'm summing up. So I can do it in columns. That's the advantage of this way of organizing data. Okay, so I'm multiplying, there is FA everywhere, so it will be A plus B plus C times FA. Good enough. So far, so good. Okay. This by B, this by C, so there will be B minus C times F prime A H. So far so good. Plus 1/2 B plus C F double prime A H squared. Nice. Plus 1/3 factorial B minus C F triple prime A H cubed. And now when I multiply OH4 by some constant, it just changes coefficients, not powers. And the same here, I add two polynomials, again quotation marks, I'm imagining just polynomials. These are infinite series actually, power series. The dominant power stays the same. So there will be another tail with totally different coefficients, but again, the important information about dominant power is here. Okay, so far so good. What was I trying to do? Oh yes, I was trying to actually find the derivative. How do I get the derivative? Well, I could try to get rid of this term, but that would just make my life more complicated. I want to see the combination of data here on the left. So let's keep the basic shape like that. Let's worry about this later. Now we will worry about this h. I don't really like it, so I'm going to divide everything by h. Here we go. A FA plus B FA plus h plus C FA minus h divided by h, okay, is equal to 1/h A plus B plus C FA, okay, plus B minus C F prime A. I like that too. Where was I? Here. Plus 1/2 B plus C F double prime A just h, because I'm cancelling one h. Yes. Plus 1/3 factorial B minus C f triple prime a h square plus o h cubed. Okay, what's really bad if you find out around here that OH cubed is not enough information, that you should have done it longer. This is really bad, but I think it's okay. I think I have it long enough. We will see. Okay, this looks like an approximating expression. Notice that all three expressions here, they look the same, of the same shape. It's the same form, so this looks optimistic. What happens when h becomes really, really tiny? Well, here I get my approximation. And this term goes to infinity. This is very bad. I don't want any infinity in my picture, of course. So what I'm going to do, I'm going to ask that this disappears. And that's an equation. Notice that I have three coefficients, a, b, c, to determine, to play with. So this is definitely a reasonable requirement. A plus b plus c should be 0. Then this term goes away. I'm happy. When I send h to 0, it does not influence this term, so I will get my derivative, which is wonderful. So another requirement is that b minus c should be 1. Definitely. That's how I want to play it. And this means that I get approximating formula for the derivative, which is wonderful. And again, let me remind you of something. Where was it? It was somewhere here. The approximation is equal to the actual value minus the error. Let's fit it. This will be my approximation when I'm done. X, that's what I want to approximate. It's over here. This is what I want. So it means that the tail over here, this part, that's actually minus the error. Just like before when we were playing with the Taylor expansion. Now the procedure is slightly more complicated, but the end result has the same interpretation. Here is what I want to use in my approximation. Here is what I'm actually approximating, and that's the difference, therefore that's the error. Okay? Now notice an interesting thing. Normally I would look at it and I would say, okay, there is error of the order of h. Very unpleasant. However, notice that I have three variables here which are available to me, which is wonderful, because I have three requirements. Requirement number 1, requirement number 2, and I have one requirement left, which means that I can ask for this to be 0. And the most dominant term, the dominant term in my error drops out, which means that the error will get smaller. And this is the key. Okay? Notice how it works. You are trying to get something out of this formula. So you spend some of your data, some of your requirements, some of your variables, but this really corresponds to the number of data that you have. So some data you spend on getting rid of parts that you don't like. And if you have enough data left, you can spend it on making the error smaller. So if I added a fourth value somehow, I could actually also get rid of another term in my error estimate, perhaps. So let's make a little inventory of what we did right here. 3 equations. 1 equation, 2nd equation, 3rd equation. Can I solve it somewhere on the side? Okay, let's solve it somewhere on the side. A plus B plus C should be 1. B minus C should be 1. And B plus C should be 0. Sorry, A plus B plus C should be 0 also as well, like that. Okay. What happens if I take the 3rd equation and subtract from the first one? I get A is equal to 0. That's very nice. I like that. So I have 2 equations now. B plus C is 0. B minus C is 1. This can be solved in any way you feel like. Let's say that I add these two. I get 2B is equal to 1. B is equal to 1/2. C is equal to negative 1/2. Now let's see what it means. A is 0. Nice. B is 1/2. And C is negative 1/2. And this is equal to this term drops out. This is 1, so there will be just the derivative. This term drops out, and b minus c is actually 1, plus 1 over 3 factorial, cubic derivative, or the third derivative, h squared, plus oh cubed. That's how it looks like. I like it. This is the error. And this, if I take number 2 and move it down, is exactly the central difference. Yeah? So what we just did, we proved that if you want to use these 3 pieces of data, and if you want to combine them as a linear combination to get the best possible approximation of the derivative, then it's exactly the central difference. So you cannot get a better approximation using those 3 pieces of data and linear combinations. The second thing that we've shown is the order of the error. We can see that the error is approximately negative 1 over 6, the third derivative, times h cubed, squared, h squared, which is oh squared. That's a very important consideration because it shows that the error decreases much faster for the central difference. If you remember, for the forward difference and backward difference, here for these two, the error was OH. But suddenly for the central difference, the error is OH squared. It's much better. It goes to 0 much faster. So our, let's say, intuitive feeling that the central difference looks better in the picture is actually borne out by calculations. Let's have a look at some comparisons. So in this picture that we will see, where's the cursor? Here. Let me enlarge it for you a little bit. Voila. What do we see? There are 2 curves which look quite different, but they sort of merge near the origin. The origin, that's the place where we want to see it in applications, very small h's. And they are almost the same. So we strongly suspect that the red curve and the the green curve are the forward and backwards difference. And that's true. The red one, that's the forward difference, and the green one, that's the backwards difference. Again, I'm using this example with exponential, just like before. Now there is a new guy in game, that's the blue one, which is the central difference. And you can see that it has a different shape. It has a shape of parabola, which this may not mean nothing actually. Why? Well, because when h is large, there will be those extra terms acting on it. So really what's important is how it behaves when h is small. So let's zoom in. And now it becomes really interesting. We are zooming in. Ah, shucks. And what do we see? We can see that these two forward-backwards differences, they look like almost like a straight line. And the central difference is curving. That's the flat part of parabola. So we can really see here nicely on this example the substantial difference between linear error and quadratic error. This is called the order of the method. We would say that the forward difference is method of order 1, and likewise the backwards difference. But the central difference is a method of order 2, and that's the major difference between them. That's wonderful. Let me put up some slides, because I think it's time that we talk about it. Okay, there is nothing new really here. What we can see here is the formulas, forward, back difference, central difference, and we can also see the error indicated like that. And that's why I could afford to put equality. So the derivative is actually equal to the approximating formula corrected by some error. And we can see the magnitude of the error, the order of the error. There is another formula for the second derivative, which brings me to an interesting question. When I have some pieces of data, I may not ask just for the first derivative, but also for the second, and so on. So let me erase this calculation, and let me just indicate how I would work for the second derivative here. Okay, the story is the same. We take 3 pieces of data, we express them using Taylor expansion, And then we are looking at linear combinations of the data. And this time we are hoping to develop a formula for the second derivative. That's our target. So I look at it and I say, okay, that's easy. I just divide everything by h squared. Okay? Let's have a look at it. A, fa plus b, that's f. A plus h plus c, f, a minus h, divided by, what was I doing? I was dividing by h squared. Should I also introduce 2? Nah, let's keep it like that, h squared. Okay, let's move on. 1 over h squared, a plus b plus c times fa, plus 1 over h, because 1 h cancels, b minus c f prime a, plus 1/2 b plus c, f second derivative a, plus 1 over 3 factorial b minus c, the third derivative, times h, plus oh squared. Now, what's my target? My target for today is the second derivative. So definitely one requirement is that this will be 1. And that gives me one equation. B plus C is equal to 2. Easy. Now, there are two terms here, and both of them go to infinity. This ratio goes to infinity. This fraction goes to infinity. I don't like it. And therefore, I need to destroy this term, and I need to destroy this term. How many requirements do I see? 1, 2, 3. That's it. So let's see how it develops. I will solve for A, B, and C. I will substitute in. These two terms will disappear. Here I will get some approximating formula, and actually that will be exactly that one. You can see the pattern. It fits perfectly. And let's have a look at the error. The error is over here. That's actually minus the error. We talked about it earlier. Now, at the first sight, it would seem that the error is actually OH, that it's a linear error, which is not very pleasant. But fortunately for us, well, unfortunately for us, we don't have any requirements left, because we have 3 variables here and 3 equations. So on the surface, it's done and dusted. But when we look at it, we actually ask that b minus c be 0. That's one of our requirements. And therefore, and this is a very lucky coincidence, this term will also be 0. And it means that the error will actually be OH squared. Now, that's a bonus. Bonus for symmetry, bonus for being lucky. Okay? I would not expect it normally, generally, because I don't have enough data to actually make my error better. But I got lucky. And that's why there is OH squared. I think you can see the pattern here. Imagine that you get, I don't know, 13 pieces of data. And let's say that you want the 10th derivative, okay? Okay, I can't resist. I apologize, but I just can't resist. So that's the 10th derivative. And you play the same game. You take your pieces of data, you expand them, you form a linear combination, and then you look here. And what do you see on the right? On the right you see something times fa, and so on. And then there is the 9th derivative, and then there is the 10th derivative, and then there is the tail. And let's calculate now. It's actually common sense. You can see that there is a pattern that you can sort of see. If you want to see the 10th derivative, which is your target, then you have to get rid of the previous terms, because they will go to infinity after you divide by h to power 10. Okay, so over here, and that's this part that corresponds to this, you will need some equations to make all the coefficients equal to 0. How many equations? 0th derivative, first, second, and so on. You need 10 requirements. Then there will be some coefficient here. I didn't write it, but you know, there is some coefficient in front of the target derivative. So you need one requirement here. and then there is the error, and normally the error will be OH, because that's the next power. After no power is the first power. After no power is the first power. Yeah, we'll be dividing by h to the power 10 and so on. However, we have 13 pieces of data, 11 requirements, so there is 2 requirements left, which means I can actually arrange for the error to be OH cubed, because h will be gone, h squared will be gone, and h cubed will come in. Okay? Or perhaps not, because of the symmetry bonus. If you want to be sure, you just keep the expansion longer in your calculations. So actually, I should have stopped with h to the power 5. If I stop at h to the power 5, I will see what happens with the next term, and I will see that it does not cancel. It will be there, so the error really is OH squared for the second derivative estimate. Okay? So there is a logic behind it. This is a very flexible method for developing estimates. Very nice. Here is an interesting question. Imagine that you want to find an estimate for the first derivative, which is of good quality, of the second order, but you have a problem because you know your function like that. This is A, and you only know your function to the right. So you cannot use the central difference. What do? Well, you make a step to the right, and you get one piece of data. Another piece of data is A, of course. And then you make another step to the right, and you get your third piece of data. And again, you find the expansions, you combine them, now things will be different because there is this number 2, it will be coming up over here. So the calculations will be different in detail, but not in substance. You can play the same game, you let some terms disappear and so on, and you can get custom formulas for derivatives. So this is a very powerful approach. I like it a lot. It shows that the Taylor expansion can really do a lot for you. Anyway. This was a little bit of a bonus, okay? We are not going to go this far in this course, but I like it so much, I wanted to tell you about it. Okay, so far for the methods. We have nice methods. We could see what's behind them. We could see the mechanism which is behind them, so we can develop more and more methods as we need them. We have a nice estimate of the errors, which is an important part in numerical analysis. And now we move to the next question. What is the next question? I talked about it in the previous lecture. Numerical stability. Because when you use it actually, you are using computers to calculate, and there are those floating point errors and so on. So how sensitive is this to floating point errors, to round-off errors? Let's think back to this fact on error propagation. Okay, what do I see? I see division. Division essentially doubles the relative error. Okay, it's not nice, but it's not a big deal. Subtraction, let's imagine our exponential. It's a positive function, so I have a positive number, I'm subtracting. How is it a subtraction? We saw previously that subtraction can be really, really dangerous if I'm subtracting 2 numbers which are similar. Wait a second, h is almost 0. If h is almost 0, then these 2 numbers are almost the same. Isn't that suspicious? The answer is yes, it's very suspicious. We are just asking for trouble with this formula, frankly. So let's have a look at it. Okay, I'm going back to this graph of our error. Okay, this is the error of the forward difference as applied to the exponential example. Let's move in and let's focus on what's happening near the origin. So now I'm looking at the range between 0 and 0.001, and it looks all right. It's getting flatter and flatter because our approximation that we saw before is really good, the one half h with negative sign. So I'm getting closer and closer to the origin, and suddenly something appears here. Well, we actually see 2 curves here, so perhaps I'm going to remove the second one. I was doing the comparison, I forgot about it. So let's get rid of this comparison business. Now we can see our curve nicely. there is something fishy happening, and that's exactly the numerical errors. So let's have a look a little bit closer. Wow. You can see that the error is really, really small, but instead of a flat curve, it becomes sort of like wavy. That's where the numerical errors kick in, and they kick in harder and harder and harder, and suddenly they totally spoil our results. You can see that the errors are much larger than the actual errors from the method. I mean, these answers here on the left, they are useless. And that's typical. Very often, when you do some numerical calculation, and you're interested in your error, as it depends on the step, you get a picture like that. If you overdo it with your step size, if you get too close to 0, then the numerical errors will totally spoil your calculations. So, of course, the best thing to do is to get this h with this smallest possible error and use it. And fortunately, we usually do not know which h is best. That's a big problem. I mean, in numerical analysis, you soon find that there are questions for which we do not have reliable answers. So one needs a lot of experience and combine various sources of information to get, well, you never get confidence in numerical analysis, almost never, or rarely you get confidence. So what you can do is to get almost confidence that your results are okay. But there's always a small probability that something went really, really wrong. And you are trying to guide against it. I mean, it requires a lot of experience to use numerical analysis properly and safely. Okay? It's not just a question of few formulas. One needs to know what can go wrong, how to work with this possibility, how to reduce it. Very important aspect of numerical analysis when you apply it to real-life problems. This is really bad. This is really bad. What can you do about it? Essentially nothing. You can perhaps increase the precision of our calculations. If you have this possibility, you ask computers to use, I don't know, double the digits in the calculations. And it will happen again, this problem, but it will happen later. So perhaps you are happy with the result which is over there on the right. Perhaps this error is good enough for a customer. So you give the customer the result over there from the right, and everything seems to be okay. By the way, this shows why the higher order methods are much more useful than lower order methods. Because the numerical error also kicks in for the symmetric difference. Let me add it here. I'm going to add a second graph, which will be the symmetric difference or the central difference. I should call it, I apologized, so okay, let me apologize again. This is a central difference, not symmetric. Central difference. And let me assign it some nice color. Let's say we had red here, so how about green or blue? Let's try blue. Blue is a nice color, I like it. Okay, as you can see, should I enlarge it some more? Is it possible to enlarge it some more? Perhaps like that. Okay, I will try this. And let's move in like that, okay? Just look at the positive part. Now, in theory, we see that the error should always be negative. So the fact that it becomes positive sometimes, it shows that really the numerical errors causes havoc. Okay? And you can also see that the numerical errors kicks in at about the same stage for both the forward difference, which is the red one, and the central difference, which is the blue one. So they are both comparable when it comes to numerical stability. They are unstable and similarly unstable for small h's. But the difference is that the central difference gives you the good enough answer much earlier than the forward difference. Let me do a simplified version of this picture for you here. And let's focus on the negative half now. Let's say that the linear error looks like this. And now it starts acting up. And here the chaos rules. Okay? Now imagine that the customer is actually interested in this precision. That's the error that the customer is, willing to accept or willing to tolerate. So if you are using the first order methods, you are out of luck because your error is getting smaller, 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 and then it becomes less reliable, and then it becomes really bad. Now, the second order method, the blue one, it actually has the same troubles with numerical stability over here in this region, but it goes to 0 much faster. When you look at a picture, you can see it. So it means that the quadratic method, it actually goes like that. And again, here the chaos starts. But the good news is that you don't have to go all the way to 0 to get a good estimate with the quadratic method. You can stop over here with your h. Here is your h. And you can say to your customer, okay, that's your estimate. Wonderful, isn't it? Okay, let's make a little bonus question now. Imagine a real-life situation. Somebody gives you a function which you can evaluate. Let's say that it's given by a formula, but it's a formula which you cannot differentiate using rules. So you end up with having to use some, let's say, central difference because you want to use the best, okay, that you have with reasonable enough data. So you pick some h. How do you pick it? That's a good question. That's a first very good question. How do you pick h? But anyway, let's say that you just pick some h, okay? You have all the h's in a big box and you close your eyes and you pick one h. You substitute, you get an estimate, you get a number. Now, is it good enough or not? That's a very good question because you do not know the actual value of the derivative. So how can you tell whether your answer is good enough or not? That's a very good question. There are some methods for it. I'm not going to ask for them at an exam here in this course because, as I said, this is a little bit shallow course. But still, it's a very good question and it's a very important question. So I'm going to add a bonus at the end of this video to talk about it because it's a general question of numerical analysis. How can you, with real-life data, with real-life information, actually get some idea of the quality of your result? That's a key question. So let's talk about it in the bonus. Other than that, I think that's about it for differentiation. As I said, this is not exactly the most useful numerical area, okay? People generally don't take functions and find derivatives numerically. This will be a building block for some other stuff which will come later for us. But I really like it because it's relatively simple. We are not using any heavy machinery, just definition of a limit, some Taylor expansions, some smart ideas which are not too difficult. And using this simple setting, we actually saw all the important features of numerical analysis. We developed a method, we analyzed the errors, and we talked about numerical stability. And usually there is also, or often there is also another step when people talk, okay, how much work do I have to do to actually get the answer? But here it's fairly simple. You just calculate the values, divide, very, very easy. There is no trouble here with work intensity needed for this. So people don't discuss it here. But just for the sake of completeness, to see the whole numerical methods package, it could be consideration with in some areas of numerical analysis.